Hi, it's K.Allen from Columbia University, and I'd like to talk to you about a system we've developed for grasping and clutter using both vision and touch. And we like to think it's a very interesting way to solve the problem, which makes grasping much more attractive.
Robots just came out called Generative Attention Learning, a general framework for high-performance multi-finger grasping and clutter using vision and touch. And basically, this is a full degree of freedom, vision-based grasping and clutter. So we don't restrict to top-down grasp or anything like that. We have multi-fingered hands. We get 92% success with cluttered unseen objects, 96% if we add tactile closed-loop grasping, which will be talked about at the end of this talk. We use a reinforcement learned attention mechanism, which we'll talk about, which lets us focus on what part of the clutter we want to attempt to grasp. And we've actually tried it on different arm-hand combinations, and it transfers very well. So it's a general method in a sense that way. And what's nice it also is does direct sim to real transfer. We do all the training in the simulation, and yet in real world results are the same as simulation. There's no degradation. So let's talk about how this works. Vision-based low degree of grasping has become successful in terms of people being able to pick up lots of objects pretty well, okay? These are just a few examples. However, this is low degree of freedom grasping. It can be limited. Parallel jaw grippers are limited to what they can do. We like to see, go back this. If you look up here, let me go back. In this video, you can see a triangle, which is a pretty simple object. A parallel jaw gripper can't do it. We made the Barrett hand into a parallel jaw gripper there because you can't really get on each side. Okay, there aren't opposing surfaces. Top-down grasping is another limitation for most of these other methods. And here you can see, because there's a depth on that top of that little chicken little, it can't get to it. So you need a grasp that doesn't necessarily have to come from the top down. And so reinforcement learning, full degree of grasping and simulation can transfer to the real world with high fidelity. So here you can see with a multi-finger grasp, a triangle is not a problem. We're able to get onto the sides and grasp. And we also know that we can do side grasps, not top-down grasps as well. So this is really increasing the range of scope of what you can grasp. How do humans do this? Well, humans basically can find what they want through attention. So you can see that every time, this is Boan Wu who wrote this paper with us, every time he looks, he's attending to where he wants to pick up using a vision. And what we want to do is do the same thing with a robot. We want to get a robot in a cluttered scene to look at things that are important and then focus in on them and then find the right grasp for that. And that's what GenerAL, this piece of work we're talking about today, essentially does. You can see here it's decluttering this table very nicely. And we'll show you in a minute that it's attending to each object individually as it does this. So how does this work? Well, we take a cluttered scene, take an image, depth map, okay, single depth map image, and then we have a 4-branch CNN with feature pyramid blocks. So basically we have position, attention, orientation of the wrist and the fingers. So the position gives me the point of attention, where we want to look in the scene that's cluttered, okay? And from the attention, we have to decide whether we want to zoom in or we want to grasp it. Okay, so maybe we can see enough to do it, or maybe we want to get closer. And what we do then is figure out the zoom scale, okay? And if we want to do that, then we're going to just zoom in and enlarge the image, get more data from it, and try this again, zooming in a number of levels. And eventually we'll do that to the point where we're ready to grasp it. We think we've zoomed in enough. And then the grasp, we'll have to go and figure out all these other positions, the wrist position, okay, and the grasp angles for the hand, okay? And these are all learned CNNs that it does through simulation. We'll show you in a minute. And from that, it can then do a pickup of the object. So what's the action space for this system? Again, we have position, which is a softmax that we sample from for training. Zoom was this Bernoulli distribution. Scale, a normal distribution. The parameters for the wrist and the parameters for the finger. So these are just the action spaces that we sample during training to get this learned CNN. The architecture is not really easy to understand on this slide, but basically it shows you there are different CNNs that are working. In the paper, we'll give you a lot more details on this. Basically, during an episode, we go and we have a fully connected network with feature pyramid blocks. We get a binary success reward. So over all these zooming, we either pick up the object or we don't. And that's what's used to balance between exploration and exploration. We use a clipped surrogate objective. So here's some video of it. You can see it working. And it attends to each object by zooming in on it and then figuring out how to grasp it through the CNN that it's learned. And again, it's a multi-fingered hand with full 6 degrees of freedom. Even though a lot of these grasps look top down, they're not exactly top down, and it turns out that makes a big difference. This is the simulation environment using PyBullet, and basically we have thousands of random cluttered scenes. We just throw out objects, 300 plus objects that we choose from, and we just throw them on a table in simulation and then have this thing learn on it, okay? And it's general enough that we can do this for different combinations of arms and hands as well. These are some of the seen and unseen objects that we have, okay? And we've tested with both of them. So here are the experimental results, okay? You can see that in simulation is in blue, real world is in orange. The results are almost the same. And this is very intriguing for us that the actual simulation transfers so much to reality. We think most of that is due to because we're just looking at geometry, and the geometry, if it's pretty good, then it should work, okay? But these success rates are very nice. We did ablation studies to see exactly what was going on here. And what we found was that pixel attentive of this blue is really the system we're talking about, where we attend to each pixel to find the right zoom level. And you can see here where we ablate, okay, and this is really the important part and the cluttered part, where we have seen objects and unseen objects cluttered. You can see the performance really degrades for each of these ablations. So for example, with a parallel gripper, which is the purple, you can see that the performance is degraded quite a bit. So multi-fingered hand helps, okay? This is red is just using the top-down orientation of the wrist, and you can see that it misses some things where you have to tilt it to get to it, okay? Without using the attention mechanism, the green, you can see that we don't do as well. When we zoom in, we do much better, okay? Non-top-down camera basically is orange, and what that means is if, instead of taking a view directly overhead, we take a view from a 60-degree angle, and it doesn't really change too much. It works about the same. And what really was exciting to us, once we got it working, we had a Barrett hand and a Staubli hand, with a Staubli arm. We said, well, if it's general enough, can we use it on a different degree of freedom hand? And so we did. We used a UR5 seed hand, which is 8 degrees of freedom, not 4 degrees of freedom like the Staubli. And we put it on a UR5, as not the Staubli, and ran the system again. And you can see it's working just as well, even though we have a different set of kinematics, a different set of finger joints, etc. And the training was the same. We just have to train for more parameters in terms of the fingers, but it worked just as well. So as you can see here, the performance is almost identical. UR5 did a little better, mainly because it has a little bit more ability to get into nooks and crannies for cluttered scenes, which is right there. And overall, it's 92% success rate, which is pretty good. But there's always a but. Where is that 8%? Okay, so why don't we get to 100? What's going on? Where does it fail? And you can see here are two failure cases where, for some reason, either this case there may not be enough friction where that grasp is. In this case, similar, or maybe calibration error, which is probably the most likely hand-eye calibration error, where you're off by a little bit with open loop grasping. We want to do better. So how can we do better? Well, we want to finish the last mile of this race with closed loop grasping. And there's been a lot of work in closed loop grasping, but most of it has been with top-down grasp only, a low degree of freedom hand like a paralogic gripper, or single-aided objects, not clutter. So we want to try to get around all these limitations of closed loop grasping. How do we do it? Well, humans seem to be able to do it pretty well. If you blindfold a human, again, this is Boan Wu, he finds it, and you'll notice that he's adjusting his hand once he finds contacts, and then says, okay, I'm going to pick this up. So that he's closing the loop with tactile feedback, no vision at all here, okay? Can robots do this? As you can see, he's got his point of contact, and then he's going to adjust the hand based upon tactile feedback. And that's what we'd like to get a robot to do. So once he gets to a search space, gets some contacts, he can adjust them to find what he wants. So that's not a good grasp, but he can improve it through an adaptive method. Here, that initial grasp was fine. Now he's searching. That would be a vision system that tells him about where it is, and then he can then adjust the grasp and do it. So this is work that we presented at Coral 2019 on multi-finger adaptive deep reinforcement. And this is a closed loop grasping using tactile only for the sensing. It addresses the visual occlusion problem. It's robust under calibration error, and we'll show you that. It works with cluttered unseen objects. It's multi-fingered with full degree of freedom poses. And it's really a performance booster to a vision grasping system. So you can think of it as, take your vision system that works pretty well, gets 90%, then when it has a failure mode, you can immediately go into that. So how does it work? So here we have cluttered unseen objects. At the bottom here, you have some tactile contacts, target object. These are showing you the tactile contacts from this Barrett hand, okay? So what we do is we collect observations from an initial pose, which you can get from a vision system. It could be an incorrect pose, but it's one that you'll get something. And we'll get binary tactile contacts. Again, we're only using binary. We're not trying to use full force or anything like that. Joint angles and tactile contact relations. And we're putting this into an action network to see what we should do. And we have choices. Should we reopen the fingers because it wasn't a good contact? No. Should we lift it? Maybe we want to adjust it. No. And then in this case, well, maybe we'll close the fingers a little bit to see if it improves. And if the answer is yes, we'll do that. And you can think of this as implementing a continuous control loop by having these small deltas of closing each time through the system. And it continues to close until it gets more and more contacts. So you see them showing up on the bottom left, okay? And it still says, what should we do? And at this point, it says, I don't have enough context to feel confident. I want to reopen the fingers. So it's going to reopen the fingers. And then it'll do an adjustment. And the adjustment is from a learned network, which we'll talk about in a second. And now we'll try again to pick this object up. And now you can see it has a better grasp. And just as the human adaptive tactile contacts to improve the grasp, we did the same thing here. Finally, we're ready to lift it. And we're done. So what's the state space for this? The state space, okay, is conformed of binary tactile contacts, finger joint angles, and some other Cartesian tactile contacts. So these binary contacts are over time steps, the 96 cells on the sensors for the Barrett hand. Okay, again, we use a 0.8 threshold for binary contact. And the inside, so it stabilizes the tactile signals. It facilitates sim-to-real transfer by simulating it and not trying to get forces out of it. And again, binary is sufficient for intelligent grasp behavior. The finger joint angles, we sample those over the 20 time steps. And it evaluates how stable the grasp is, how closed each finger is, symmetrical contacts, and enables smart finger reopening by looking at all the data from the joint angles as we go through the training. And finally, for tactile contact positions, which are Cartesian positions through the kinematics of where each sensor is, we can get information about how stable the contact is it an opposing contact, enables new position look ahead, and we're able to go through that. Okay. So the action space here, the finger movements, we move them a little bit. And it simulates continuous motor control. It closes the sim-to-real gap. And it's a tight loop during training. And we gradually decrease the delta as training success rate improves so we can make it a more continuous control. The end effector adjustment is whether to reopen the fingers and then adjust the end effector pose. The position is adjusted center of all tactile centers. Orientation is learned. So we're able to say if we have a contact on the side of a finger, we can move it to the center of the finger. And the end effector adjustment is whether to lift the arm and end the episode. And the insights there is it learns to lift and close the loop for grasping. So for optimization, it's a balance between exploration and exploitation. I won't go too much into this, but down here at the learn milestones, this is really what it learns through this training. Don't lift under a small number of contacts. Lift only under rich opposing contacts. Don't close the fingers without contacts. So if you make contact with the finger, keep it there. Regrasp under few contacts and close grasp. So if you close the fingers, you don't make contacts, you're going to reopen it. You regrasp until good tactile contact locations show up. And then you learn the good orientation position on the new position during regrasping. This is all learned. And again, we use a similar training set as we did before, where we simulate in PyBullet, throw out on the table these objects. We make an initial guess of where to go, and then we use the tactile to improve it. And we learn all this tactile data in simulation and then match it against the real world. So we're going to compare this with what you saw earlier with the system we built that used vision only, an open loop control. Same object clutter set up in robot, same initial grasp position. So the vision system gives us a grasp position. We go to it, okay, and we use either GenerAL or at that point, we just leave vision alone and we simply try to use the tactile closed loop feedback. And what we're going to do is we're going to perturb each of these grasps Okay, so if we give a position for a grasp, we say, okay, it's gonna be a little off. And this is a way to simulate the error, hand-eye calibration error you'd see typically in the system. And we'll see how well it does. So you can see here, we perturbed it, and using the first vision system, it didn't work. So now we go to MAT, where it's gonna try to find a good grasp, and you can see it does a very nice job. Some of these grasps work right off the bat, but if they don't, then we can do the readjustment using MAT, as you can see here. It slides out a little bit, it's perturbed, but we're able to use the tactile contacts to bring it back into play. Again, same thing here. Keeps looking, finally finds it. So this is important. We want to show you some results with different amounts of calibration error. And you can see that if there's 1 centimeter error in your hand-eye calibration, you're going to do 15% better. 2.5 centimeters, 35% better. And at 5 centimeters, you can do 65% better. And you can see that the baseline here is our system we showed you earlier, which is vision only. And you can see here the improvement is pretty dramatic as you lose calibration error, particularly in cluttered scenes. So let's just do more ablation kind of studies and understand how well it works. Let's assume we use a noise-free, highly calibrated camera. And it still will have some mistakes, but you can see the improvements aren't dramatic, but they are improvements, okay? But it's doubtful you're going to have that highly calibrated camera. It's a simulation. In the real world, you can see it gets a little worse. What we did is did a comparison against the baseline of GenerAL, which is a closed loop system with a single object only, not clutter. Okay. Yeah. Hello?
Yeah.
Yeah. And you can see the improvement is pretty good here, especially when you get to 2.5 centimeter grasp perturbation. So this is just an ablation study showing you where we have MAT, which is the blue, and then we disable the position adjustment or the orientation adjustment, the finger closing, the regrasping, and whatever. And you can see that each of these has the ability to improve it. And we get 10 to 20% success rate gain due to synergies. So with a slide grasp, you can see it also works too. It adjusts, so we don't have to worry about just top down. So the key takeaways: full degree of vision-based grasping and clutter, 92% success rate with clutter unseen objects, 96% with tactile. We use reinforcement learning. It's arbitrary across high degree from hands, and it does direct sim to real transfer. It's closed loop, adaptive tactile feedback at the end. And these are my co-authors who helped me do this and did a wonderful job. And I will thank you and give you back the screen.
Thank you very much.